Good day, everyone. You are welcome to Scholars Universal School online class. We'll be treating electric field for this week. Now, in our previous class, we have discussed about fields generally, and we rightly define field as a region or space where some physical agencies are felt. And we have discussed about the gravitational field and a bit of the magnetic field. So, for the purpose of this week, we'll be discussing about electric field. An electric field is a region or space where charged bodies experiences an electrical force. Like we said in our last class, that it is just a region around an agency, just a region around. So for an electric field, it's just a region or space where charged bodies experiences the force exerted by another charged body. Now, the electric field is created by charged bodies only. Now, it is possible we have a charged body and we have a neutral body. So, electric field is usually created only by charged bodies, and it is also affected by the electric field. Now, like we have rightly explained in our previous class, that we can have two types of field. You can have two types of force. It could be a contact force or a force field. Now, electric field is also an example of a force field. Now, we're talking about, since the electric field is a force field, it is usually represented by lines of force to show the direction. It is a vector field. We have rightly discussed that we can have a scalar field or a vector field. Now, since the electric field is a vector field, it must surely be represented by lines of force. Now, the electric line of force is just an imaginary line drawn in an electric field in such a way that the direction at any point gives the direction of the field at such point. So if I have a line showing the direction of the electric field, the line is obviously telling you the direction in which the electric field will follow. Now, we can equally define electric line of force as a path which an isolated small positive charge. Now, those small positive charge is also called a test charge. We make use of a positive charge as a test charge always in an electric field. So when I bring a small positive charge into an electric field, the direction in which that small positive charge follows represents the direction of that field. Now, this diagram explains the path of an electric field. Now, all the lines with arrows that we can see here explains the direction of the electric field. Now, we rightly see from the diagrams we have here that we can have a positive charge or a negative charge. Now, we can see the field line patterns around two unlike charges. Now, you will see that here we have two negative charges which are obviously repelling each other. Now, we see the line of force that it is moving out of the negative charge. Now, same thing you will see when you see that of the positive charge. The lines of forces are moving out. They move outward from the positive charge. Now, so if I draw an electric line of force without telling if it is a positive or negative charge, by just the direction of the line of force, we can obviously see the direction, we can obviously see the type of charge that we have there. So if it is a positive charge, the line moves outwards. Then if it is a negative charge, the line moves inwards. Now, we obviously want to talk about the properties of field lines. Now, the first property of field line is that the field line would only start on positive charge and end on negative charges. Now, from this previous diagram that we have here, we'll see that the electric line of force for a positive charge points outward, and that of a negative charge points inwards. So it's as if the positive charge is giving out the charge and the negative charge is receiving it. So we would obviously see from this previous diagram. Now, the second one is that line of force do not cross each other. Now, every of the examples of diagrams we have here, we'll see that the lines of force have a specified pattern in which they are following. They do not cross any of the line of force that we have around it. Now, the third one, he said in a uniform field, line of force are straight, parallel, and uniformly spaced. We can have a uniform field and we can have a variable field. Now, every of the fields we have here are uniform. Now, since it is a uniform field, the line of forces are uniformly spaced. Now, the next one is the line of force indicate direction of electric field. I think I've explained that before, that the line of force for a positive charge is showing that the charge is moving outwards. Now, for a negative charge, it is moving inwards. And the last one, the lines are drawn so that the electric field is proportional to the number of lines crossing unit area. Now, the closer the lines we have here, the stronger the electric field. That is what it means. And the more the line of forces that we have here, the stronger the electric field. So if I have just one line of force, it is going to be a weak electric field compared to when I have more than one electric line of force. Now, we would now be going to the electric current. Now, like we rightly said from the beginning of this class, that electric field is usually caused by charged objects, by electric charges. Now, those charges could either be at rest or they could be in motion. Now, when charges are at rest, we speak of what we call static electricity, like the word implies, static electricity. Now, when the charge is in motion, it is referred to as current electricity. When charges are in motion, we refer to it as current electricity. Now, for the purpose of this class, we'll be talking about electric currents. Like we have talked about before, electric currents would be when you have charges in motion. So majorly for the purpose of this class, we'll be dealing with electric currents. As the class goes on, then we'll go to static electricity. Now, electric current is defined as the rate of flow of electric charges along a conductor. So meaning that electric current, like we have said, it is a charge in motion. So the rate of flow of these charges along a conductor is what we call electric current. Now, we said a stream of moving charges constitutes an electric current. We have said that when charges move, they constitute electric current. Now, mathematically, we can describe the flow of charges by expressing it in terms of quantity of charge and the time it takes for the charge to move along a conductor. We have defined current to be rate of flow of charges. So we can mathematically give an expression to show the relationship between the quantity of charge and the time it takes for the charge to flow along a conductor. Now, the quantity of charge is measured in coulombs and the time is measured in seconds. So hence, we can give current mathematically to be the quantity of charge divided by the time taken for the charge to flow in the conductor. And the unit of current is ampere. The unit of current is ampere. It is measured in ampere. Now, we can have some other submultiples of ampere, some smaller multiples of ampere. The same way you have meters, kilometers, then smaller divisions of meters will be your centimeters and your millimeters. So the same thing we have for your current. It could be measured in smaller quantities. Now, we could have smaller multiples of your ampere, which is your milliampere, and that is your ampere raised to the power of your ampere times 10 to the power of -3. Now, for current, we have an instrument that is used to measure the amount of current flowing in a circuit. And the instrument used for measuring the amount of current flowing in the circuit is the ammeter. It is called ammeter. Now, in case we have smaller currents that the calibration of the ammeter cannot read, we also have some smaller measuring equipment that can measure that, and that is called milliammeter. It is used to measure smaller currents that the ammeter cannot read. Also, we have some very small currents that the milliammeter also cannot detect. Now, to measure those very small currents, we use a very sensitive instrument, which we call the galvanometer. So the galvanometer is used to measure very small amount of current, then the milliammeter for smaller currents, then ammeters will be used to measure large currents. Now, an ammeter is said to be sensitive. There's something we call the sensitivity of an ammeter. Now, an ammeter is said to be sensitive if it detects or measures very small currents. And an ammeter is said to be accurate if the current it measures is close to the exact value. So you could be asked to define the sensitivity of an ammeter or the accuracy of an ammeter. Now, we have described that the electric current is charge in motion. Now, there must be a path in which this charge will be allowed to move. Now, the path in which electric current flows is what we call electric circuit. The circuit is the path provided for flow of electric current. Now, the circuit consists of a lot of electrical appliances. It could be your battery, it could be your wire, it could be electric bulb, which is the load, the key or switch, which allows the circuit to be closed or open. It breaks or makes the circuit, your key. Then we could also have some other electrical appliances and components. We will talk about that very soon. Now, other components could be the ammeter, which is used to measure current flow. Now, the voltmeter also is used to measure potential difference. In a short while, we'll be talking about the potential difference. Now, we could have the resistor, rheostat, which is used to adjust the flow of current. We'll get to understand every of those other components as we go on in the class. Now, these are examples of the electrical component and the electrical symbol. You can see the electrical symbol for your cell, electrical symbol for your resistor, that for your battery, for your switch, for your capacitor. Now, every of those components would be used, every of this diagram would be used to represent all these components in an electric circuit. Now, these are more examples of electrical components. Now, we have the voltmeter, the galvanometer, which we said is used to measure very small amount of current, the ammeter, the bulb, we have the fuse, which is used to make or break a circuit. Now, hence we'll be talking about types of electrical circuits that we can have. Now, majorly, we have three types of circuits. The first type of circuit we're talking about here is the closed circuit. Now, this is a path given for electric current to flow. Now, a closed circuit is the kind of circuit in which there is no gap. The key is usually closed. When we say there is no gap, it means the key or the switch is closed along the conducting path. Now, in such a circuit, the current flows through an external load. When the circuit is closed, current flows through an external load connected to the battery or the cell. Now, the second type of electric circuit is the open circuit. Now, the open circuit is a circuit with a gap or opening, meaning that for the open circuit, the key is open. Now, once the key is open, there is no current that would flow through that electric circuit. So, for an open circuit, the key is open, as the name implies, open circuit. So, for a closed circuit, the key is closed. For an open circuit, the key is open. And in such a circuit, the battery maintains no current in the external load. And the bulb we have here would not light up. As compared to your closed circuit, the bulb we have in this circuit would light up once the circuit is closed. And the third type of circuit is what we call a short circuit. Now, a short circuit is also an example of a closed circuit. But in those type of closed circuit, you have no external load. Comparing the short circuit with your closed circuit, you would see that for your closed circuit, you have a bulb which serves as the external load. And comparing with the short circuit, you have no load, which is the bulb in your short circuit. Now, we have defined electric current initially to be charge in motion. This is a diagram of ammeter. Now, the ammeter usually connected in series in a circuit. Now, we'll be talking about how ammeters are usually connected in an electric circuit. Remember, we have said ammeters are used to measure electric current flowing through a conductor. Now, ammeters are always connected in series in a circuit. They are connected in series in a circuit. Now, we'll be talking about something we call potential difference. The potential difference between any points in an electric field is defined as the work done in moving a positive charge. Remember, we have said that a positive charge would be what we call our test charge. Now, the work done in moving a positive charge of one coulomb from one point in an electric field to another is what we call potential difference. Now, the potential difference is an essential condition for the flow of current. Now, we'll give an example of the flow of water through a pipe. Now, if the pressure between the two ends of a pipe are the same thing, the water would not flow through the pipe. There must be a difference in the pressure between both ends of a pipe for water to be able to flow through a pipe. Now, same thing is applicable to an electric circuit. There must be a difference in the potential between a point and the other point before electric current will flow in an electric circuit. So potential difference is actually an essential condition. It is very necessary for current to flow in an electric circuit. There must be a difference in the potential between two ends before current would flow in an electric circuit. Now, the potential difference is measured in volts. That is the unit of the potential difference. Now, we'll define another term which we'll call the electromotive force, E.M.F. Now, the electromotive force is the total work done in driving one coulomb of electric charge round a circuit. Now, the difference between electromotive force and the potential difference is that the potential difference is just the work done in taking a charge from one point to another point in an electric circuit. But the total work done in moving that charge round the circuit is what we call electromotive force. It can also be defined as total energy per coulomb obtained from a cell or battery. Now, it is mathematically given as the work done divided by the quantity of charge. The work done, which is in joules, that's the unit of work done. The work done in joules divided by the quantity of charge flowing through that electric circuit. So EMF is given as work done over charge. Now, this is the mathematical expression V equals W. Your V is going to be your electromotive force, your EMF, measured in volts, equals to your work done measured in joules divided by the quantity of charge measured in coulombs. Now, we'll be talking about the measurement of PD and the EMF of a cell. PD would mean potential difference. Now, the instrument used for measuring potential difference across 2 points along a conductor is called a voltmeter. The voltmeter is the instrument used to measure the potential difference or the electromotive force in a circuit. Now, like we rightly said previously, that ammeters are usually connected in series in an electric circuit. Voltmeters are connected in parallel. They're usually connected across the points where you want to measure the potential difference. So voltmeters are connected in parallel along, it is connected in parallel across in a circuit. Now, voltmeters are constructed in such a way that they have very large electrical resistance. Now, in the course of this class, we'll still be talking about what we call electric resistance. Now, this is a diagram showing the connection of a voltmeter. A diagram showing the connection of a voltmeter. Now, we can see that the voltmeter is used here and it is connected in parallel across this resistor. We have shown these electrical components to be what we call a resistor. This is the electrical symbol of a resistor. Now, as compared to your ammeter, which is connected in series, your voltmeter is usually connected in parallel across the components you are measuring. Now, we'll be talking about what we call conductors and insulators. Now, conductors are materials which allow electricity to flow through them easily. They allow currents to flow through them easily. Now, examples are almost all metals in pure water, water that has impurities inside of them. Pure water would not conduct electricity. So impure water could contain a little bit of salt solution or maybe an acidic solution. Now, impure water allows currents to flow through them. Now, other examples would be inorganic acid solution, damp air. All these are examples of conductors And the best metallic conductor is silver, followed by copper. So meaning that the best bet of metallic conductor you can find is your silver, followed by copper. Now, on the other hand, we have insulators to be materials which would not allow current to flow through them easily. They do not allow currents to flow through them easily as a result of the high resistance they have to the flow of current. They have high resistance, and conductors would have very low resistance. That is why they allow currents to flow through them. Now we're talking about what we call resistance. As the name implies, resistance. Now resistance is defined as the opposition to the flow of charge or current. Resistance is the opposition to the flow of charge. Now, any opposition offered to the free flow of charges in an electric circuit is what we call resistance. And the unit of resistance is what we call the ohms. Now, this is the symbol of ohms. Now, your resistance is measured in ohms. So, like I said earlier on, insulators which are very bad conductors have high electric resistance, and conductors which allows current to flow through them easily have very low opposition to the flow of current, and that means that they have very low resistance. Thank you for learning with us at Scholars Universal School Online. Conductors which allows current to flow through them easily have very low opposition to the flow of current, and that means that they have very low resistance. Thank you for learning with us at Scholars Universal School Online.